So here we are, part 2 for chapter 6, object modeling. Now, in this phase, we're going to look at UML, the Unified Modeling Language, which is essentially a set of specific symbols to represent graphically the various components and relationships within a system. Now, if we use this consistently, it doesn't matter which project we're working on, we suddenly have a unified language that everybody understands, easy to understand because it's a graphical representation of business functions or processes that happen within a system. So an external entity which is outside the box of the system, and as we'll see, I'm going to give you another component that really helps. It's called a boundary, and we'll look at that and where that is in the boundary. So external entities sit outside the boundary. They're everything or everyone that might interact with what's going on within the system. Okay, so external entities are called actors. They initiate use case by requesting the system to perform a function or process. So consequently, there's going to be that link between them. Okay, so here's an example. So symbols for use case is an oval. So that's the use case. Okay, with a label that describes the action or event. So this is the use case. And of course, this is again another black box. We don't really know what goes on inside here. We just know that inside here is something that's going to be capable of making an airline reservation. And the actor or external entity in this case would be labeled passenger. So a passenger would make an airline reservation, or here that message here would be, might be even make airline reservation, so we don't need to necessarily put it twice. Now the use case itself should be an action-oriented thing. Make appointment, change pickup address. So the actor is shown as a stick figure with the label. Now, when we build a complete use case, what we would do is put a boundary around the use cases. So the use cases are within the system. So we'd put a box here so that we could clearly see that the actor sits outside of the system. Okay, so a student is going to be added to a fitness class. So there's a use case called add fitness class. Produce fitness class roster comes from fitness class. So once we add a fitness class, we're able, so the produce fitness class roster uses add fitness class, the information from add fitness class to create the roster. Same thing here, update instructor information, change availability, same kind of thing. Okay, now again, documentation associated with the use case. So in this case, add new student. That's really the use case title should tell us exactly what it does. In this case, it does. The actor involved, student manager. Description describes the process used to add a student to a fitness class. So successful completion, how if the use case is completed, or an alternative. So if the class is full, what do we do? Those kind of things. So you can see a precondition to this is the student requests fitness class. That means the student needs to be a student in the system before they can request a fitness class. So there might be even additional preconditions that must be met. So they're just giving you one, for example. And postcondition, they're registered in the fitness class and fees have been paid. So somewhere in this add student is the ability to pay. Now what we see is just like with our context diagram, how we explode that. We're going to explode these use cases down to their functional primitive till we create a use case or a process that may have many use cases that build that complete process. So by doing this, we create a use case diagram. It's a visual summary of several related use cases. There we go, within the system or subsystem. And the first step is to identify the system boundary. So that's what I was talking about here. It's simply a rectangle that represents the boundary or border of the system. So here's a great example of a use case diagram. So it has many use cases. So when we talk about a UCD, we're talking about a diagram of many use cases. Normally, of course, use cases that are related. Okay, So you can see how one use case leads to another, results in another. So auto service, customer requests service. Well, that's going to create a work order. The service writer is going to write that work order. That work order is going to be updated to a couple places. Okay. It notifies the mechanic who's going to do the work. So update the work schedule. So the create work order is going to update a work schedule. Remember, this work schedule might be updated from work orders. It might be updated from other things that a mechanic needs to do once the mechanic performs the work. So you can see that there's directions into the use case and out of the use case back to the actor. So inputs and outputs. So create a bus route. Here's another example. Student initiate, create requests, forecast. So students are saying, hey, I need a bus here, etc. That's going to lead off to a dispatcher who is going to basically do some work, may do some manual work here. There might be a sub case here where they store all the work, all the requests, etc. That then prepares a plan, route. They create that route, they develop the staffing plan, and the people involved are notified, such as the driver notified who to pick up, when to pick up, how to pick up, etc. So class diagrams shows the object class and relationships involved in a use case. Okay, so we're going to create class diagrams from those use cases. We've already talked about what classes are, so we've really covered part of this as we create that diagram. So each class appears as a rectangle with the class name at the top, followed by the class attributes and methods. So lines show the relationship between the classes. So how are they going to interact? And a diagram also includes a concept called cardinality, which describes how instances of one class relate to instances of another. So cardinality, you might have heard me say in part one, like one to many, for example. Okay, so here's the UML notation for this. Okay, and nature, so 0 to many. Okay, or 1 to many, for example. So 1 to 1, 1 to 1, 1 to only 1. You can see that, 1 to many. Okay, so that's one way of representing that cardinality, that relationship between. So an employee, okay, can have many payroll deductions, not just one. Okay, 0 to 1, an employee, okay, can have no spouses or one spouse, for example. So you get the idea. You could figure out the other two. So as we look at this, let me be clear on your homework, and I'll send out a reminder of this with the weekly schedule, with the weekly video. On your homework, what I want to see is something like this, but I actually want you listing the specific attributes and methods. So if it says a few, it means 3. If it says a couple, it means 2. So keep that in mind. I want to see multiple attributes and multiple methods, okay, for the object that you're creating. So you see here a sales rep, okay? One sales manager can manage many sales reps, okay? A sales rep can be assigned to only one sales office. A sales manager manages only one sales office. However, a sales rep can be assigned to many customers, okay? And then a customer can place many orders, and each order can have many items. So that's a way to represent so that we can start defining the rules of the system. Okay? What that also, by the way, allows us to do is know how many of these objects we're going to end up instantiating inside the system. Okay? So an order can instantiate many items, many item objects, and item objects, with all of the attributes and methods of an item. For example, when we assign an item to an order, it may kick off a method, check inventory, right? Make sure that the item is in inventory. If not, it may kick off a method to order from vendor, for example. So you can see how very complex and interrelated these things are. So a sequence diagram, it's a dynamic model of a use case showing the interaction among classes during the specific time period. So how is this stuff going to go down, as it relates to time? Is it over a short period of time, a longer period of time, etc.? So we'll see an example of that here. Graphically documents the use case by showing the classes, the messages, and the timing of the messages. So include symbols that represent classes, lifelines, messages, etc. So here's a class. This is its lifeline, how long that object is going to exist. Okay, before we may do something like store it back in a database, then we're done with that object. Okay, so lifeline, you can think of it as the time it stays in memory. What's going to happen during its lifeline? Well, it's going to send messages maybe to other classes, maybe to things being done. Okay, and then the focus identified by a narrow vertical shape that covers the lifeline. You can see that. Okay, indicates when an object sends or receives a message. So a message, if you notice, is going to be sent to class 2, and class 2 is then going to respond, and that's what ends that class's life cycle until it's instantiated again, maybe to do something. So this could be, say, a calculator object, and class 1 sends some information to a tax calculator. It does the function that it needs to do. It returns. We don't need the tax calculator left open in memory, right? Creating a buffer overrun and potential security issues. So consequently, we just kill that class. So its lifeline is to there, as you can see. Now, if that's something we're constantly using, we might keep it open and clear the information that's in there and be ready to process additional information through that object. That way we're not having to use the resources to close it and reinstantiate it and close it, those kind of things. So you can see, focus. So a student requests a fitness class. The manager might check the schedule, fitness class schedule. Now, I don't really buy this because then once they check it, they would go back and notify. So there really should be a line here saying class is available. Okay. And then, of course, behind there, well, what if the class isn't available? We're still going to notify the student. The student then pays, and the registration goes through. So if you look at this, a lot of this is being automated, right? The manager is being taken out. The student is making the request to some system that's checking the class, making sure it's available. It's notifying the student that yes, it is, so you can sign up for it. Student signs up for it, pays. Once they're paid, they're put on the registration for that class. So a record is created. Hey, they've paid. Okay. Now, we've sort of seen this before. State transition diagram. We've seen this. We could think about this as a sequence diagram in a little bit. What happens if this is true and this is true, we do this. If this is true and this is false, we do that. Similar type of thing here. However, what we're talking about here is an object whose state changes. Okay, so we, an account is open. That creates a new account object. Okay, well, once that first deposit is made, that new account object. So in this system, they're saying we can actually create a new account without an object, perhaps. I mean, without a deposit, perhaps. Okay, so that we're ready for that first deposit. And of course, we do that because that way we open an account and our first deposit comes with our next paycheck. Well, once that happens, that account becomes active or is existing. Well, what can be done with an active or existing account? Well, assets attached, well, frozen, customer closes account, bank closes account. Somehow the account sometime in the future is going to be closed. It could be that many things happen during this active state. And also, once it's closed, we may pull those records that relate to closed accounts out of our production system, for example, so that they're not taking up rows and records inside a database that have to be stored through. So another example is a customer needs cash. They insert the ATM card. Here we're going to see some variance. The card is accepted by the ATM, so it's, like on their star network or whatever the case may be. Customer enter PIN. PIN is accepted. Now, if you think about this, this state diagram would definitely want something off of here that says customer enters PIN. PIN is not accepted. What are we going to do there? So you can see from there, we're going to do something else. Normally either re-enter the PIN. That process may iterate 3 times, and then we may take the card. So the ATM may take the card, in which case the person has to go to the bank and get the card back. So that protects somebody if their card is stolen. Someone puts it in an ATM and tries passwords. They can't sit there all day and do it. But in this case, the state just talks about if the PIN is accepted and requesting cash. So we request cash. Well, first of all, if there's sufficient funds, they do a balance transfer, and ATM provides the cash. So the cash is debited from the person's account, and the cash is provided. If there's not sufficient cash to make that withdrawal, the ATM notifies the customer. Customer gets the opportunity to maybe reiterate back through this process. Reiterate back through this process to request a balance. So notifies customer, may say there's not enough money in the account to make that transaction. Would you like to try another transaction? In which case they'd come back through here to the request cash and follow along with that procedure. So business process modeling, BPM as we call it, represents the people, events, and interaction in a system. So outside rectangle is called a pool, and it designates swim lanes, show specific actions and events. So swim lanes can interact when certain events occur. So here is an example. Now, we've talked about this before, right? A business process. So, here's something, there's a task that happens. You've probably seen this, in your life at some point, even if it was a joke, of, well, what happens if the student passes? Well, they go here. If they don't, they, stop here. So business process modeling is a great way. It's easy for people to see, where the process starts, what tasks are involved, a true-false direction. So, if true, go here. If false, go here. If under 500, go here. If over 500, go here. So you can see how complex this suddenly becomes as we use all these tools to define and graphically represent the system. So object modeling requires many types of diagrams. Yes, it does, to represent the proposed system. If you think about it, we'll have a use case diagram that's going to explode into some sequence diagrams. A use case itself may have a sequence diagram that represents everything that can happen in the use case. For example, a customer, wants service done. Well, what happens if we don't have anybody to do that service? Well, we go out to the next day. We find an available slot because we know that service takes 2 hours. Well, the quickest we can get you in, like at a doctor's office, well, it's May now, and we can get you in for your first appointment in July, that kind of thing, because we're just so booked up with appointments. So what would happen if we could create an appointment? What would happen if we don't? Show availability. You can see how all of this stuff is interrelated and how we can greatly reduce process flow once we have these. If we see some redundancy in there where, where like this case comes back to this case and they go back and forth, the question is why? Or if there's a deliverable that's produced that goes out to an actor that then, comes back in the system that goes out to the actor again. We have the ability through these diagrams to see places where we can produce or eliminate certain inaction or infunctionality in a system. So lean a business process. A great example of that would be, well, we only have one part shed or one part storage area within our manufacturing plant, and people are constantly running back and forth to get parts. Well, maybe if we distribute that part storage area, maybe that becomes the main distribution facility. But then at each manufacturing location, we have a place for parts that are going to be used that day. Then the employee doesn't have to walk back and forth all the way across the deal every time he or she realizes they need another part. So as much as these case diagrams can be used inside a system, okay, so an employee in this case, opens a case. Well, when they open a case, help desk gets involved, it gets added, okay. There's the case can be closed and ended, most cases opening, so notify that a case is opening, they analyze, etc. So it just depends on what happens in the system, okay. So as much as I was saying, as much as these can be used to design a system, a lot of these tools can be used to look at physical business processes that are going on that may need to remain physical in a system and unify them or lean them out. Okay, so organizing the object model, develop an object relationship diagram that provides an overview of the system. So we may have these huge objects that become subclasses of that object, right? Organize your use cases and use case diagrams so that they can be linked to the appropriate class, state transition request. A lot of times we'll have documentation on each of these diagrams that says, this is related to this use case. So as you look at this state transition diagram, go find the documentation on this use case. Sometimes they're one-to-one entities, sometimes they're multiple. So it's much easier to repair a diagram now than change the software later. That's why we create these, folks, is again, we can take this back out to the end user, back out to managers and say, this is what we understood the process to be. Is this correct? Because if we build software based on a bad process, all we're going to do is make that bad process worse. Or as I like to say, make that bad process faster. Faster bad. So a great example of that, at a company I worked for, we had a thing called an NCR, a non-conformance report, and we were generating about 10,000 of these non-conformance reports a month in the manufacturing process. Anything that was out of spec from the original design had to go across a non-conformance report before the product could be manufactured. So consequently, you could see a great deal. They were hand writing these things and hand running them around the plant for people to sign off, for engineers to check, for our governing body to approve of the change, etc. So consequently, this was a great way to improve or automate that process by putting these all in a database. That way we could also get information out, things like, what thing was creating the most NCRs, so we could get engineering working on, the items, the manufacturing engineers to work on items that were having the largest impact on our company. However, because this wasn't in the database yet, we didn't have that information, right? So someone could certainly go through, create an Excel spreadsheet, documenting what each one was and then searching through that, but you could see the advantage. However, the base business process before automating that into software was just really poor. These things were going from one person to another, back to another person, back to that person, back and forth. It was estimated that each one of these things, by the time they were written up and completed, were costing the company $500 each. Okay, that's mostly in labor, in transfer, in slowdown of manufacturing, because, well, gee, I can't put this part on until I get the NCR that says I can. So manufacturing or production stops. So by automating the process, we were able to increase that. However, because, like I said, the process was essentially so cumbersome before a system, what I wanted to do was put the brakes on. Let's start leaning out these processes, so when we build a system that will work, it's working on a leaner business process. So you can imagine, in some cases, folks, creating a business process diagram that we talked about, we might do that in 10-point font and it would fill the size of a pool table, for example. a 10-point font in small objects. So you get the idea of the sheer complexity of that. And by doing that, we are able to see that there were places that we could change the current business process and create a better system. However, got in that funk of, well, we need it yesterday. So we started building the system. We spent 8 months on this system at over $200,000, and we implemented it, and it was so complex and so hard for an end user to understand what the system was doing that it lasted less than a month in manufacturing. What happened? Well, we threw it away and started again. The next time we did it, it was successful. Now, we had all of our documentation. We went back, we leaned the process, we brought in some lean manufacturing engineers who were able to look at the process and say, well, let's cut this out. Let's do this when we do this. That way it doesn't have to go back and forth. We cut out this time and this delay. And the next time we did it, the system was implemented correctly. So here's an example of, we need it yesterday. We don't want to take the time planning. Had they have taken the time and planned, we wouldn't be doing the process again. We wouldn't have a whole new team on it. We wouldn't have spent twice the money to get the job done one time. So hopefully this makes sense. Thanks for watching. Have a great day.